Okay, any questions? Are you, I mean, this is not something you expected, right?
Well, yeah, I
This is
didn't
something, yeah, no one expects this. It's like the Spanish Inquisition. No one expects the Spanish Inquisition. So that's a Monty Python reference. You guys are too young for that. All right, so let's go and discuss our next topic, which is the solution, the formal solution to the Schrödinger equation. So suppose I give you a state at some time 0. Okay. State of system at time t equals to 0. And I ask you what happens to the state at a later time. Okay, so you will have to solve this, solve the Schrödinger equation for that, right? So we want to solve the Schrödinger equation. So let's write this again. Now the Schrödinger equation, let me just suppress the x dependence. So this is the equation of time t. And we just know that at time t0, psi becomes this, this thing. So let me introduce a time evolution operator. And what it'll do is that it'll take my state at time 0, and if I apply this operator, let me call this operator u. If I apply this operator on the psi, it gives me the state at a later time. Okay, so this is the definition of the time evolution operator u. Okay, let me just write this. The time evolution operator u of t does this. Okay, so we assume that our Hamiltonian h is time independent. That means that the potential energy is just depends on space. It doesn't depend on time. If the Hamiltonian, if we take a Hamiltonian which is time dependent, the solution is a little bit more involved, and the formal solution involves something called the Dyson series, which is not something we will get into in this course. So under this assumption, what happens to this equation? So this equation becomes I h d by dt u of t psi at time t0 equals to h u of t psi at time 0. Okay? Now, we assume that the time evolution operator does this job for all psis, not just a particular psi. That means this equation is true for all psis. Now, this equation is true for all psi. So that means that this equation must hold as an operator equation. So we can write this equation as I h bar du. Let me just because there's no space dependent, so I can write this as dut by dt equals to h, and that's it. Right? So this is pretty easy equation to solve, right? So it's going to be d of u of t. It's an operator equation, so we can write this as h minus I by h bar d of t, and therefore log of u of t is going to be minus I by h bar h hat of t plus some constant. And if I take the antilog of both sides, I get u of t is some constant, c prime, which is the exponential of this guy, e to the power minus I by h bar h hat of t. Now, the fact that, at time t0, psi must be equal to psi naught, that means that u at time 0 must be the identity operator, right?
Sir, shouldn't there be a U at the right hand side of H, like in the first line?
Yeah.
And then
So you're right. So there should be u of t, and there should be let's just say and then there would be a u inverse of t. Yeah, sorry about that. Okay, thank you. So this is telling us, because if I go back to my boundary condition, it is telling me that at time t0, this thing must be equal to this thing. So at time t0, this thing must be the identity operator. So if I use this, then this implies that C prime is just 1, or the 1 or identity operator, it doesn't matter, C prime. So U of t, the time evolution operator, is given by e to the power minus I by h bar h hat of t. So what does this mean? It's an exponential of an operator. What it means is this. It means it's a power series. The first term is just identity operator. The second term is minus I by h bar by factorial 1 h t plus I by h bar. Sorry, let me put the t. Let me just write this. I by h bar t squared by factorial of 2 h squared plus dot. Okay? Okay, any questions?